Hello everyone. Starting from this week, we will discuss the graph theory. And since we don't have homework assignment anymore, so I remind you to focus on the reading report. And also this week, the lectures will be shorter than usual since last week we overtime. Okay, and graph theory. So recall, actually, when we discuss the Ramsey theorem, we define some notion in graph theory. Let's recall some part of it. So a graph G. So this is a so-called simple graph. Later on, we will introduce a more general, which is called a general graph as a generalization. So a graph is composed of two types of objects. So vertices, or in some specific field, they call it nodes, V, and each element is a vertex. And then you have another type of objects called edges. So here inside is pair of distinct vertices. So here, later on when we do some generalization of graph, this condition can be dropped. In that case, you will have a loop. Also, here, you will see just in a moment that for an edge, there's no direction. That means from x to y and from y to x, we view them as the same thing. But later on in the next chapter, when we discuss a directed graph, we will include more information on the edge. So x goes to y is different from y goes to x. Both cases have practical use in our daily life. So we first start with a simple case without any direction. And we would like to use a notation G equals V, comma E to present the graph. Okay, next we introduce more definition for the graph. So first thing, what is the order? Graph G. This is defined to be the cardinality of the set V. So recall the set V is consisting of all the vertices, and therefore the order just the number of vertices in G. And there are another group of notations. So if alpha equals xy equals yx is an edge of G. Recall that when we do the definition of the edge set, we mean that each element is a pair of vertices, and the pair has no order. Therefore, here xy is the same as yx. Okay. This is by definition. Then we say alpha joins x and y and that x and y are adjacent. This is clear from geometry, and we also say that x and alpha, or similarly y and alpha, are incident. In other words, one of the vertices of alpha is x. So this is the most rigorous way to explain what does incident mean. But actually, when we do proof, or you see the textbook or some journal paper, they will be very short, very concise, use the notion incident. And x and y are the vertices of the edge alpha. So each edge has two vertices. Okay, now let's look at some example here. Suppose G is VE. V is given by a set of A, B, C, D, E. E is A, B, B, C, C, D, D, A, E, A, E, B, E, D. So here you have A, B, C, D, E. If you draw the picture, it looks like this. Okay. Next, we generalize the notion of simple graph to the multi-graph. From the name, you can guess it has a similar meaning as a multi-set. So allow a pair of vertices to form more than one edge. So multiplicity of an edge is the number of times mxy occurring in E. Okay, and actually in the following, the most common notion we are going to use is the general graph, which allow loops on the base of the definition of multi-graph. In other words, for any pair of vertices, you can construct any number of edges between them, and also this pair, the vertices in this pair, the vertices in this pair can be the same. Then in that case, you will have a loop. I will draw some pictures. So for it, probably just a remark, that is graphs the set of all graphs, simple graphs, is a subset of multigraphs, is a subset of general graphs. Therefore, general graph is more general objects, suitable for more problems. Okay, now let's look at the following example. Suppose you have 4 vertices and draw edges in this way. Then we'll say this is a multi-graph because you don't have loop. And then if you consider the following one, which is called Ghostbuster. So here, the dot part means the vertices, and all the edges can either between distinct points or just between the same points, just like this one. This is a loop, starting and ending at the same point. Therefore, this is a general graph, which is not a multi-graph, not a simple graph. Okay, later on we will come back to this picture again. And in this case, actually, we already discussed some special graph, simple graphs before, that is called complete graphs. And for example, this is K1. This is K2 and K3, K4, and K5. And here's a very important phenomena is that here you have intersection of the interiors of edges. This is This is not a vertex of interiors of edges. Is not a vertex. So whenever we say vertex, or you draw that in the graph, probably we need to use some thicker dot to present it instead of just intersection. And why this is important? Because not every graph can be drawn on the plane perfectly without no interior intersection. So it's not easy to prove, but people can do that, showing some graph, for example, K5 cannot, no matter how you draw it, on the plane, there must be some interior intersection. The intersection point is not a vertex. It's not a vertex. Okay. So just a remark. So we call a graph planar if it can be drawn on the plane without interior intersection of edges, and not all graphs are linear. Okay, next we turn to another useful notion that is called degree of valence. So degree of valence of a vertex X in a general graph G is defined by degree X is the number of edges that are incident with X. So in other words, this is the cardinality of the set or Y such that X, Y is an element of the set E. And for each point, you can attach this invariant and arrange degrees of vertices of a graph of order n, d1, d2, dn, and d1 greater than d2, greater than d3, greater than dn, greater than or equal to 0. So we call this degree sequences of G. Okay, immediately we have the following theory. Let G be a general graph. The sum d1 plus d2 plus all the way to dn of the degrees of all the vertices of G is an even number. In particular, the number of vertices of G with odd degrees is even. So actually this theorem consists of two parts. And for the first part, we write out the sum in another way. So we sum this in the following form. For any edge E in the capital E, in the set capital E, it contributes degree 2 to the total sum. Okay, therefore this is a sum of even numbers. Finally, this is even. And for the second part, we rewrite the summation in the following form. Suppose we split that into two parts. For even di, we have a partial sum, and then next we have a order di, summation of order di's, dj's. And note that this is always even. Therefore, this must be even. And for a summation of order numbers to be even, then the total number of summands in the summation should be even. Therefore, we complete the proof for the second statement. Okay, after we introduce several interesting invariants attached to the graph, we define the following notion of the isomorphism of grass. So two general graphs G prime are called isomorphic, provided that there is a one-to-one correspondence theta from V to V prime, such that for each pair of x, y in V, there are as many edges of G joining x and y as there are edges of G prime joining zeta x and zeta y. So how to understand this? Actually, if you think about what is isomorphism of two linear spaces, so that means you construct a linear map and there's no kernel, no co-kernel. The dimension is same. And here, suppose you have graph whatever. Suppose you have graph and let's call this as A, B, C, D. And then you have map theta. So here you will have theta A, theta B, theta C, theta D. And so for example, if AB, there are one edge, AB, between A and B, then if theta is isomorphic, then there should be only one edge between theta A and theta B. And similarly, you will have this. And if you graphically, mathematically, so here you have V, so A, B, C, D, and then on this side, V prime should be zeta A, zeta B, zeta C, zeta D. This is not always case. You can construct arbitrary map theta such that V prime either consisting more vertices than the image of theta, or you have some redundance here. And also for the edge, here you have AB, BB, BC, AC, 2CD. It's a multiset, and AD, 1, 2, 3, 4, 5, 6, 7. Yeah, totally have 7 edges. And then you map to this side, and then E prime should be theta A, theta B, zeta B, zeta B, zeta B, zeta C, zeta A, zeta C, 2 zeta C, zeta D, zeta A, zeta D. Okay, and if you are confused by the definition, just compare it with the isomorphism between linear spaces and do some nature guess what is a correct way to require the morphism theta. The bottom line is that forget about how it draw on the plane or how it represented by the graphs. As soon as you have G and G prime, you know they are isomorphic to each other, then everything you know from from G can be recovered from the information of G prime and vice versa. And therefore, in particular, you will have we will use this to denote G and G prime are isomorphic. If they are isomorphic, then order of G is the same as order of G prime. Notice that order is an invariant. And then the coordinate of E is the coordinate of E prime. And the degree sequences are the same. Blah, blah, you have many more. And an interesting property is that from all the invariants on the right-hand side, most of the time it insufficient to determine the isomorphism. This is a typical phenomena in the invariant theory. Why we want to know invariant? Because invariants, in some sense, capture the main difference among different objects. But on the other hand, since when we find invariants or use invariants to formulate a problem, we usually take the most easy way to derive the invariants. Therefore, most of the time you omit something. Okay, therefore, most invariants are not enough to determine the whole system. Whenever you have such a theorem says certain invariants capture all the information, then that invariance will be very, very important, or the objects will be very rigid in our sense. In mathematics, there's some rigidity theorem which shows in certain category, when you have certain objects and only by certain invariants you can recover all the information. So those type of theorem called rigidity. Okay, the importance of the isomorphism can be illustrated by the following theorem. Let's draw two graphs. Okay. Both consisting of 4 vertices and 6 edges. And someone already recognized that this is a complete graph K4. So although on the plane it looks quite different, but essentially they're same, isomorphic. Therefore, if you want to study the property of the right-hand side, for instance, it suffices to look at the left-hand side, because left-hand side, some sense it's easier, you don't have interior intersection. Okay, another example is given by this one. Suppose you have 4 indices, 6 vertices, and you draw like this. And the question is, do we have isomorphism between this one and the hexagon? Notice that inside the hexagon, the interior intersection is not a vertex. And this is already not that trivial. Although you can compute the number of edges, whatever. And how do you find that? So the answer is no, they are not isomorphic. And then the reason is that on this side, you have a complete K3 as a subgraph. We will explain what is a subgraph just in a moment. And on the other side, no complete K3. And the remark is, in general, to show G and G prime are isomorphic, it suffices to construct an isomorphism. While to show they are not, G and G prime are not isomorphic. Usually people don't enumerate all the possibilities to show that they are not isomorphic. What we usually do is find some invariants, distinguish them. So for example, in the above case, one cucumber way to show that they're not isomorphic is say, suppose A is mapped to A prime, blah, blah, whatever, what conclusion you can draw, and B mapped to B prime, what conclusion you can draw, enumerate all the possibilities, just like you just act like a computer to test all the cases. For example, here, so remark. Let's call this example star. Star, we can test in this way. So here you have A, B, C, D, E, F, 6 vertices. Here you have, let's see, U, V, W, X, Y, Z, 6 vertices. And then you test for all possible theta. So all possible means you just pair randomly, such that each one on the right hand side is mapped to one point on the right hand side, and test all the possibilities. Okay, and then draw the conclusion they're not isomorphic in any case. Okay, but this is too difficult usually and time consuming to do that, and therefore the usual way we do is find some invariants, just like a knife, not that big, not that deep, but just stab in your heart, just kill the person. Sorry, it's too brutal, but the problem is like, the key point just like this. You find, for example, here, you find the complete K3 on the left-hand side, and also test that there's no K3 on the right-hand side, then you're done. You don't need to do any test anymore, because if they are isomorphic, something on the right-hand side must appear on the left-hand side. Okay, next important property, which we will also use study later. This is called the connectivity. So suppose G is a general graph, and a sequence of M edges of the form x0, x1, x1, x2, xm minus 1, xm is called the walk or length m, and this walk joins the vertices x0 and xm. And we can also denote this walk as x0, x1, x2, xm. And we introduce some notation. We call this walk a closed walk if x0 is xm. We call this is open and otherwise. And we call this walk a trail if edges are distinct. And we call this walk a path if you have distinct vertices. Especially, in particular, a path must be a trail, because if you have repeated edges, you must also repeat the vertices. And here, except possibly x0 equals xm. So if you have walk, you call it a path. If there's no repetition of vertices, except finally you come back to the beginning starting point. At that case, we call it a cycle. So this is called this is a case closed path. And to illustrate the different notion, we'll look at previous example of the Ghostbuster. So so because here we will have a quantitative discussion, therefore we denote each vertex by letter, alphabetical letter, A, B, C, D. Okay, then A, D, E, M, K, I. If you go through this, will be A, D, E, M, K, I is a path of length 5. Note that you have 6 points, but only length 5 because you have 5 edges among the vertices. And then you have, let's look at A, D, B, D, H, G, H, M, K, I. So this is a walk of length 9. So A, D, B, D, H, G, G, H, M, K, L. And you can see here we have repeated the edge BD. Therefore, it's not a path, not a trail. So it's just a walk. And then you have A, D, H, G, H, M, K, I. So A, D, H, G, H, M, K, L. So notice that between HG you have 3 edges. Therefore, you can choose different ones so that there's no repetition. So this is trail of length 7. And now if you look at the case DE or DEFE, MHD, DEFE, MHD. This is a trail. This is a closed trail. But it's not a cycle because you repeat some vertices. And which one is cycle? EFE. This is a cycle. EFE. This is a cycle. Okay, and next, following from the notion of work, we can define a connected graph. This is for x, y, for all vertices x and y exists work joining them. And here actually equivalently, you can find, if you can find a work join them, you can find a path joining them. It's not that easy, but I leave it to you to show this. Okay, then otherwise, if there's a pair, you cannot find any work join them, then we call it's disconnected. And you can define distance for vertices x and y. We can define the distance dxy by the minimal gamma work joining them length of gamma. In other words, you find the work joining x, y with the least length. And the first thing is dxx is 0. And second thing is dxy is an integer. In this sense, later on we will introduce weights on the edge. So in that case, you might have a different value. It might not be an integer. But here, actually, you can view the weights are uniformly 1. So it's an integer. And then if dxy, the distance between x, y are finite, in other words, there's at least one work joining them, then exists a path gamma joining x and y such that distance is realized by the length of gamma. So this gamma might not be unique, but at least it minimizes the distance. So we call gamma a minimizer of the distance. This is very important because if you have infinite graph, or more general, you have functional in mathematics, computer science, in math, statistics, not always you can find a minimizer. You need a lot of conditions to guarantee a minimizer. But in this case, we always have a minimizer because of the property that the distance is an integer. And now let's look at one interesting example. Suppose you had you have the following graph, and you will see that this is actually disconnected. Although when you draw the picture, it's connected, but from the point of view of graph theory, it's not. Because the connectivity is an intrinsic property. And here, for this one, definitely you can, it's isomorphic to the following one. Okay, now we can introduce a notion of subgraph. So suppose G is a general graph, and let U be a subset of V, and F be a multiset of E, such that the vertices of each edge in F belong to U. So this is to guarantee G prime is also a graph. G prime is defined by UF is also a general graph called a general subgraph of G. Why we call it subgraph? Because all the information of G prime is included in G. And for some special case, we have a different name. So we have some final realm. If F consists of all edges of G that join vertices in U, then G prime is called an induced general subgraph of G, and is denoted by GU. So this case called induce. So induced actually means you only need to know U. So what does this mean? Actually means U plus G. It suffices to define G prime. You don't need to know the information of F. So that's why we call it induced. And secondly, if U equals V, G prime is called spanning. Okay. You can view this as a human being. They have the same bone skeleton, but then just lose weight after hitting the gym. Okay, and then we have the following very important theorem, which shows that for any graph, even it's not connected, you can decompose it into several pieces, each one such that each one is maximal connected. So suppose this is a general graph, then V can be uniquely partitioned into non-empty parts V1, V2, Vk, so that the following conditions are satisfied. So first, G1, G2, Gk determined by V1, V2, Vk are induced subgraphs are connected. Secondly, for each I different from J and vertices in Vi, Vj, there's no work that joins X and Y. Probably it's good to illustrate by some graph. So suppose you have graph and like this. Okay, what we are doing is just decompose this graph, and this is a G1 piece. This is a G2 piece, and then you have G3. Okay, so how to prove it? You have many ways to formulate. I would like to choose the following one. So by a maximum, so take a maximum set of points x1, xk, such that for each xi different from xj, there is no work joins xi and xj. So here maximum is in the sense of the set containment. Okay, you have partial order, so this is maximum. This is not trivial, you need to prove it. So in the proof, you need to use a graph is a finite set. Okay, after that, so define Vi to be the set of all points such that there's a path joining x and xi, and then let ei be edge E such that the vertices OE are in Vi. Okay, then you can prove that Gi defined by VIEI satisfies requirement in the statement. And immediately we can define such G1 to Gk are the connected components of G. So why we decompose in this way? Because for some problems, I should say for most problems, study of the connected components and glue them up together can give you the whole information of G. In other words, it suffices for most problems. It suffices to study connected general graphs instead of the graphs with several connected components. They are same thing. in the difficult level. And immediately, a consequence from the study of connectivity is that if G and G prime are isomorphic, then G is connected the same as G prime is connected. And secondly, G has K connected components is the same as G prime has K connected components. And then G has a cycle of length K is the same as G prime has a cycle of length K. And then G has an induced subgraph Km, the same as G prime has an induced subgraph Km. So that's really the topic we are interested in graph theory. We are not interested in the plenary graphs or something drawn on the picture. We are actually studying the isomorphism classes of graphs. Okay, we care about the intrinsic properties. So just like here, in the serial graph theory, in graph, G and G prime are the same. There's no difference in graph theory. Okay, and a natural question is, since we care about the intrinsic theorem, so do we have a pure data-based description of graphs? In other words, can we forget about the picture? Okay, the answer is yes, and it's easy, although not that efficient. So this is called adjacency matrix. So for a graph G with order n, suppose you have m versus a1 to an, and define alpha ij by the number of edges joining ai and aj, and then the matrix for I from 1 to n, j from 1 to n. This is called the adjacency matrix. And for example, if you have K4, the matrix is given by 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. And very important, you can verify it very easily that GVE is uniquely determined by the adjacent matrix. In other words, suppose you have two graphs with two adjacent matrices. To verify they are isomorphic or not, you only need to verify that after permutation of the matrix, are they isomorphic? So remark 2, G corresponding to alpha ij, G prime corresponding to beta ij, alpha isomorphic to, G isomorphic to G prime is same thing as alpha ij is equal to beta ij after certain permutation of the matrix. Okay, I will not talk too much about what is the definition of permutations. If you have interest, you can work out examples, work out on the examples of K3, K4, or whatever. Or you can just look at the linear algebra textbook. Okay, and the advantage, there are another advantage that is the notion of adjacency matrix can be generalized to directed graphs. Note that alpha ij is a number of edges joining ai and aj. If there's no direction, alpha ij is the same as alpha ji, no direction. Therefore, this is a symmetric matrix, and if there is direction, alpha ij can be different from alpha ji. Okay, I will stop here for this lecture. Next time we will discuss Eulerian cycle.